You know, getting a spacecraft into orbit, it's just one of the most extreme engineering challenges you can imagine. Every single component has to be unbelievably reliable and ridiculously lightweight. But for decades, there was this hidden problem lurking deep inside their power systems, a component that was absolutely essential, but also a huge headache for engineers. And there it is. I mean, look at this. This is straight from a 1977 NASA handbook. So the problem here, it wasn't the flashy stuff, right? Not the rocket engines or the delicate solar panels. It was transformers and inductors, the magnetic components that manage electricity. And you gotta remember, in space, every single gram costs thousands of dollars to launch. So having the heaviest and bulkiest items in your power system, yeah, that's a really, really big deal. So you're probably looking at these things and thinking, why? Why were these simple-looking bundles of wire and metal such a massive challenge? Well, it all comes down to the absolutely brutal demands of just trying to operate in space. See, down here on Earth, if you're building a power supply, you can kind of cheat. You can over-engineer it, make it a little bigger, maybe slap a fan on it, no big deal. But in space, whoa, no way. There is absolutely zero room for error. A failure isn't just an inconvenience, it's game over, mission over. So everything has to be unbelievably reliable, incredibly lightweight, and hyper-efficient, because any wasted power, it just turns into heat. And getting rid of heat in the vacuum of space, that's another giant headache all on its own. Okay, so all of this pressure, it basically forced engineers into a corner. They were stuck with this fundamental dilemma that seemed totally impossible to solve. They had to choose between two absolutely critical things: size and efficiency. And this just lays out the choice so perfectly. Okay, option one, you could use a material that lets you build a really small, lightweight transformer. Awesome, right? Saves a ton on launch costs. But the catch was, it was way less efficient. That means it pumps out more waste heat, and you're risking a total component failure. Or option two, you go with a super efficient material, but now your component is big and heavy. It was a classic engineering catch-22. You just couldn't win. So why this trade-off? It all boils down to the physics of these magnetic materials. And we can actually see it in this chart, which is called a BH curve. The easiest way to think about it is like a material's magnetic personality. Some materials have a really high peak, meaning they can handle a ton of magnetic energy in a tiny package. But yeah, they're not very efficient. Others are incredibly efficient, but have a lower peak. So you need a much bigger, heavier core to get the same job done. All right, so imagine this. You're an engineer. You've made your choice, you've accepted the trade-off, and you've launched your spacecraft. Everything's going great. But then something unexpected happens. A tiny imbalance in the electronics, maybe a sudden power surge. What happens when that magnetic core gets pushed just a little too far, right past its limits? The answer? It's a catastrophic failure mode called core saturation. And what that means is, all of a sudden, the component that's supposed to be carefully controlling all the electricity just stops working. It basically turns into a simple piece of wire, a short circuit. And just like the NASA handbook says, that leads to these massive voltage spikes and huge currents that would just completely fry the sensitive transistors in the power system. This was the silent killer they were up against. So, faced with this impossible problem, what did the NASA engineers do? Well, they came up with a solution that was it was so elegant, so brilliant. And the best part? It wasn't about inventing some new miracle material. Nope. It was about using what they already had, but in a totally new way. And here it is. This is their brilliant idea. They literally took two different kinds of cores and nested one inside the other. So you've got the small, super efficient, uncut core on the inside, and then wrapped around it is a larger, less efficient cut core. And that little cut is actually a tiny air gap. And boom, together they act like one single component. Okay, so here's the genius of it. This design gives you the best of both worlds. See, during normal operations, just the small, efficient inner core is doing all the work. It's light, it barely wastes any power, it's perfect. But the second a power surge hits and that little inner core gets overwhelmed, it saturates. Bam, the outer core instantly wakes up and takes over the load. Yeah, it's not as efficient, but who cares in that moment? It can handle that massive spike of energy, soaking it all up and protecting all the other electronics from getting fried. I mean, this is really the perfect way to think about it. They created a component that runs at peak efficiency all the time, but has this built-in, totally automatic failsafe. It's a magnetic circuit breaker that just kicks in the exact instant it's needed. Absolutely brilliant. Problem solved. Now, what's so cool is that this super clever solution from the 70s, it didn't just stay in space. Those same principles of managing magnetic fields, of balancing efficiency and size, they became the absolute foundation for the tiny, powerful electronic world that we all live in today. So, we went from these big hand-assembled parts for the space shuttle to these tiny little shielded inductors. But the core idea, it's exactly the same. It's all about shaping those magnetic fields to squeeze out every bit of performance while keeping them small and stopping them from interfering with anything else. These little guys are the workhorses in everything from your laptop charger to the electronics in your car. And the miniaturization just gets more and more mind-boggling. I mean, look at this. This is a multi-layer inductor, and it's smaller than a single grain of rice. You've got dozens of these things inside your phone right now, and they're all doing the same fundamental job as those big, clunky NASA transformers from back in the day, just making sure every little chip gets exactly the right power it needs as efficiently as possible. And we've moved way beyond just winding wires around a core. Today, these things, thin-film inductors, are made with the exact same process used to make computer chips. It's called photolithography, and that incredible silicon-level precision is what lets them operate at the crazy high frequencies we need for things like Wi-Fi and Bluetooth. And guess what? It doesn't stop there. The evolution just keeps going. The next big thing is something called planar magnetics. And here, the transformer isn't even a separate component you solder on anymore. No, it's actually built right into the layers of the circuit board itself. This is going to give us even more efficiency, even tighter integration. It's really pushing the boundaries of what we thought was possible. So think about that journey. We started with this bulky, heavy problem inside a 1970s spacecraft. And from that came this elegant solution that literally paved the way for the sleek, powerful devices we all carry in our pockets today. It's just such a great reminder that sometimes the most important innovations are the ones you can't even see. So it leaves you wondering, right? As we keep demanding more and more power in smaller and smaller packages, what's the next invisible breakthrough going to be?
Please like, share, and subscribe for appreciation and such more learning friends.